Let's talk about beam analysis, exactly what you wanted to learn about today. So a beam is a structural member that carries a load that is applied transverse to its length, and you are going to have pencil icons here, so just relax for a minute. Beams are used in floors and roofs. They might be called floor joists, stringers, floor beams, girders, and this person's jumping. Beams are designed to carry the shear and bending moment caused by the design loads. A bending moment is sort of this thing that causes the beam to bow down. That's what a bending moment is. So more on that in just a second. What we're going to be doing is chasing loads. So loads are initially applied to a building surface, the floor or a roof, and then the loads are transferred down and then out to the beams, out to the girders, and then to the columns, then all the way down to the footings. So the first thing that you're going to write down is just a definition of static equilibrium. This is a state of an object in which the forces counteract each other so the object remains stationary. That means that no matter what all the forces are, this thing is not moving. And a beam must be at static equilibrium to successfully carry loads. The loads applied to the beam from the floor roof must be resisted by forces from the beam. The loads applied to the beam must be resisted by forces from the beam supports. That's these ones down here. The resisting forces are called reaction forces. So having a little picture of this is sort of the significant piece here. You have this beam, you have reaction forces in the bottom, and you have the applied load on top. Reaction forces can be linear or rotational, and we'll more about this in a minute, so you don't have to write this down. But these linear forces are called shear, and reaction or rotational, are called moment reaction. So we're going to be doing solving problems that involve both of these. The methods of support dictate the types of reaction forces. So as we looked at with our bridge unit, there are some that have rollers, so that when the bridge expands, and so you still have this upward vertical force, that's Fy. You have pinned connections. When you have a pinned connection because of expansion, you can have a horizontal force. That's why there's an F of X force here. And then with fixed supports, that gives you a moment. If it's attached here, then the load in the middle will cause this thing to bend down. And that's why you have this moment reaction force that we're showing as opposite to that. So one thing that I do want you to write down, we have 6 different beam types. So I want you to draw a picture of the simple beam. So we have this with the arrow here, a vertical arrow. So these arrows show you the forces that we're going to be using. We're going to be focusing on simple beams. Continuous, pretty straightforward. It's just a few more upward forces. A cantilever, this is sort of a unique one, so make sure you make note of this. It's fixed at one end, so this extends out. So it really is only one upward force, but then you have this large rotational force, because if you have a load on this end, it's going to be kind of bending down right here. And here's your other 3. You have a fixed one, which is a double rotational force in here because it's fixed on both sides, moments at both ends. And then you have one that's propped up, so it's attached on this side, fixed on this side, and then one that's an overhang, so kind of like a cantilever, but it's supported a little bit further into the structure. So I just want you to draw these out so that you at least have an illustration of how they look. For simple beams, and this is what we're going to be looking at, you'll have a fixed spot and an applied load somewhere generally on top of the beam. So it's going to be our beam diagram. And when there's no applied horizontal load, you can ignore this horizontal reaction at the pinned connection. And largely that's what we're going to be doing. We're not going to have horizontal loads. We're just going to have 2 fixed edges, and we're going to have a downward force. So in sum, the fundamental principles of equilibrium say that the sum of, that's what this symbol means, mathy people, the sum of the forces in the y direction, that's the up-down direction, they have to be 0 if that thing is not moving. The sum of the forces in the x direction have to be 0 because they're not moving. And then the sum of the moments, that's the rotational stuff, they have to be 0 because this thing is in equilibrium. So the sum of all these forces have to be 0. That's going to be sort of the key in how we solve these problems in the next videos that you're going to watch. So to end this, we're just going to look at the definition of moment. It's created when a force tends to rotate an object, which we talked about before, and the magnitude is equal to the force times the distance. Force times distance, that is moment. So I think you've seen this in a physical science, a physics class, if you're in that. If not, now you've seen it. So it's force times distance, that is the moment. That is a calculation that you're going to have to do, is the load here, the force, times this distance. And you will see more on that when I teach you how to do these problems in the next videos. Rocket fuel.